Now let's talk about the conditional randomization assumption, which will let us weaken this very strong total randomization assumption that we were working with before, and let us make causal inferences in settings where we don't actually have that total randomization. So randomization is super, super strict, right? To require that these potential outcomes are totally independent of A, which is typically accomplished by saying that A is totally randomly assigned. It's like a coin flip, right? To get that, you need to have strict control over that assignment mechanism, and basically by doing an experiment, right? Or assuming that A is being out in the real world is being assigned randomly, which is pretty crazy. Usually people are getting treatments based on who they are, what they look like. I mean, in a medical setting, right, you're not going to give somebody a drug if you don't think they need it. It's not like people are randomly just flipping coins and handing out drugs, or assigning people. If you're asking about like how does pollution affect people's health outcomes, it's not like people are randomly choosing to expose themselves to pollution or not. Certain people live in certain areas, or because of structural inequalities, are exposed to pollution that other people aren't. And the point is that is structural and not random, right? So this randomization is a super strict assumption. You're basically saying there's no arrow going from X to A. And in the real world, that's just not the case. Most of the data are observational. We have all sorts of factors here, genetic, socioeconomic status, places where people live, that, in this example, like let's say we're asking about smoking and lung cancer, which we seem to think that there's a causal link, but for a long time that was in question. A lot of people were fighting back against that because there had not been randomized studies that were done, and they're saying, hey, it could just be there's some underlying factor that people who happen to like to smoke also happen to be predisposed to lung cancer. And none other than our friend Ronald Fisher, who we talked about when we did hypothesis testing and p-values. Fisher was a prolific smoker, and he thought that there was actually some kind of shared genetic structure, or at least in the softest setting, that the effects of smoking on lung cancer were not all due to the smoking, but that genetics somehow played a large role. And obviously he was pretty wrong about that. But my point is that it was a debate, and the reason it was a debate is because people were saying, hey, there's no randomization here. How can we actually know? There's all this confounding. So how do we get around that, right? And one of the most common ways that people get around that is to make a weaker assumption, which is not, well, it's not strictly weaker, but most of the time it can be thought of as weaker, which is conditional randomization. So instead of assuming that the potential outcomes are independent of the exposure, we're going to assume that we've also measured some baseline variables. Typically, we'll call these covariates, and we're going to assume that the potential outcome and the exposure are independent in each subgroup or each stratum of the population defined by these covariates. So, for example, this could be, age is often a confounder, or chromosomal sex, zip code, things like that. So we're saying within, if this exposure is, let's say, pollution or something like that, and our outcomes represent the rates of asthma, then we might say, okay, for people who all live in the same neighborhood, who are the same age, and have had the same kinds of life histories, perhaps, the exposure can be considered to be as good as random, right? That's kind of the idea, and I'll show you why this helps. So it's actually very similar to the proof that we can identify the causal effect with randomization. The only difference is now we have to condition. And this is a common kind of trope, is like you have some kind of identification proof that works in a very strict setting, and you can generally relax it by just conditioning. So first step is we use total expectation. So this outcome this mean potential outcome that we're after, we just use total expectation to say it's the expectation of the means in the subgroups defined by X. And now that we're in here, if we believe this conditional randomization assumption, then we can just stick an A in there, because the distribution of YA given X is the same as the distribution of YA given X and A equals A if these things are conditionally independent. And now, by definition, in the subgroup where a equals little a, y little a is the same as y. So we saw this before, but for example, if you're talking about the subgroup of treated people, the potential outcome that we observe, y1 is y, because that's the definition of y. Is for the treated people, we get to see y1. For the untreated people, we get to see y0. And so here, if we have a 1 here and 1 here, then these two things are the same. y1 is y in this subgroup. So I can just transfer this, and now we have something that has no potential outcomes in it, right? This thing in the middle here is the expected value of y given x, a equals a. This is some function of x. So you tell me a population stratum, and I'll give you this mean in that stratum of the population. So that's what this function does. It tells me what is the mean of y in this stratum of the population for each treatment group. So the stratum is defined both by the population and are you talking about the untreated or the treated in that group? And this is what we call the observable ATE. We just have an average over those subpopulation averages to get at this thing. So no potential outcomes. So this is something that we could actually estimate from data. You could estimate those subpopulation averages and then just aggregate them. Key thing here is to notice that this is the expectation over the marginal value of x. So for example, so if x is a binary random variable, then we would write this as mu y xa times the probability that x equals 1 plus that x equals 0. So notice here these are marginal probabilities. They are not conditioned on a being a. So like the how much we're weighting these subgroup means depends on how prevalent this subpopulation is in the population, not something like this. Okay, that's sometimes confusing. Okay. So yeah, like I said before, the assumption here is that you basically have good as random assignment within each stratum of the population. Now this is contingent, well, we'll talk about this more in a second, but this is contingent on you being able to measure enough stuff here in X, right? Because like, let's say you just measure age, but you don't measure zip code. And you're telling me, okay, within 18-year-olds, the exposure to pollution is independent from the outcome, their asthma status in 5 years if they had all been exposed to pollution. I'm going to say that's probably not true, right? Because there's a lot of variability within 18-year-olds, and you know if you're not like zip code, right? If you're not also conditioning on zip code, there's going to be the people who live in zip codes that are more highly exposed to pollution are also going to often be poorer, right? And so they'll have higher rates of asthma because of that, not because of this pollution as well. And so you're going to have that kind of confounding that you're not conditioning on it, right? In here. So if you don't have enough strata, if your strata are not actually capturing that confounding structure, then this doesn't hold. So all of this is contingent on having enough stuff here measured in X. And here I just wrote X single variable, but this is really standing in for X1, X2, X3, so on and so forth. All of this works the same. So I also want to mention that what I'm calling conditional randomization has a lot of different names. So if you start reading the literature, you're going to see unconfoundedness, you're going to see no unobserved confounding, as good as random. This is kind of where I'm trying to sit. Random assignment, it's a little confusing because it's conditional, right? Ignorable, exogenous, conditionally exogenous. X satisfies the backdoor criteria. Selection on observables. You'll probably see all of these at some point. All of them are trying to say the same thing, which is just this, okay? It means you've observed enough stuff that in each stratum of the population, you basically have a randomized trial. So let's dig a little bit more into the intuition. This is just mechanical, right? Like I just showed you it works, that I can get from this mean potential outcome to something that you could calculate from data. It's a little more it's more complicated, right? In the randomized example, the all we had to estimate was this conditional mean, right? Easy. That's just one sample average. This is a little more complicated because we have to estimate a sample average in each subpopulation and then weight them and combine them, right, to get to this. So it's a little more complicated, but nonetheless, the overall idea is the same, which is that we've come to some number that we can actually calculate from data without actually observing all of the potential outcomes, which are, of course, impossible to always observe. So that's great. But it's very mechanical. I just showed you algebraically that it works, and I want to give you some intuition for why it is that this conditional randomization is nice. So let's go back here to this picture where we're plotting some covariate, maybe age or something, the potential outcomes for a equals 1 and a equals 0 case. So each person here has 2 dots. What would have happened to them if they got the treatment, and what would have happened if they didn't. And so their kind of like individual treatment effect is the length and direction of this dotted line here. And so the true average treatment effect is the average difference between those two, or the kind of average value of the gray dots, which is maybe here, minus the average value of the pink dots, which is here, or vice versa. So if we look at the observed outcome, so this person we get to see y0, these two people we get to see y1, so on and so forth. If we have confounding, this creates problems because if we take just the average of these people and just the average of these people, it's going to look pretty similar. I mean, just eyeballing it, right? I think we already looked at this. They're going to be pretty similar. But what we can do is look at this conditional mean. If we knew what the conditional mean function was, so let's say we knew this mu y, which I was calling mu y, or here expected value of y given x equals 0. So you can think of it like this: at a given point, little x, you take the group mean of the people in your population who were treated and have this zip code or this age. Let's say this is like 18-year-olds who are treated. What's their average outcome? And then this is 18-year-olds who were not treated. What's their average outcome? Right here, so this is 18. You do the same thing for 40-year-olds. 40-year-olds who were treated. 40-year-olds who were not treated. Okay, so that's what this graph is showing you. It's continuous here, but you can imagine just discretizing it into bins like that, like 18, 40, whatever. And that gives you the right intuition. So that's what these conditional means are. So if you have those, you can then impute what the potential outcomes what the outcomes would be for every value that you observe in your data set. So instead of taking the average of your observed values, you can just say, okay, well, look at this person here, right? What would their value have been if they were treated? What would their value have been if they were not treated? What about this person? Same here. But now the nice thing is that for the people for down here, right, you get these circles where before you did not have those data points, right? You didn't know what was going on down here. But because you know this conditional mean function, you can kind of fill in those values by guessing that they're going to be on that conditional mean. And same for the gray, right? All your observed data is just over here. But you want to know what's going on over here because you want to compare. You don't want to compare this to this. You want to compare this to this. So you're going to kind of fill in those dots by pretending that they fall on the conditional mean function. And then the difference in the average between those gray dots and the pink dots are what you're going to estimate as your observable ATE. Or another way to think of it is like the average difference between these two lines, where what you're averaging over is the distribution on the x-axis. So let's do this here. This is similar to what we saw earlier. Imagine this is the entire counterfactual population. First, is A independent of y0? I hope you can see that that is not the case, because in the A equals 1 group, we have 2 1s in the y0 column, but in the A equals 0 group, we have just 1. And actually, y1 and y0 are the same. So in fact, in this situation, there is the treatment actually has no causal effect, right? Because for this person, they would have had the outcome anyways, no matter what. For all these people, they don't have the outcome no matter what. So there actually is no causal effect here, okay? So let's add a column indicating the observed outcome. So here, let's just say that's not the case. The observed outcome here is going to be 1. Well, it's y1 and y0 are the same, so I can take out the 1. This is the observed outcome, right? Expected value of y0. Let's do this one first. That's 3 and 3, so that's 1/2. The expected value of y given a equals 0, so that's average of this value, and this value, is 1/3. So those are not the same, all right? And in fact, we already said the treatment effect here is 0, exactly, right? But if I compute y given a equals 1, that's this number, this number, and this number, it's 2/3. So if I just looked at this data naively and compared the difference in outcomes between the two treatment groups, I would say that the treatment effect is 1/3, when really it's 0. So that is no good. However, let's imagine this is the population, okay? And now the same population, actually, I haven't changed anything. The question is now, is A independent of y0 given x? So in each stratum of x, is the distribution of y0 the same for the treated and the untreated? So what we have to do, let's look at the x equals 1 case first. So just draw a line here. So we're just looking at this part of the table for x equals 1. And we can see that the distribution of y0 and y1, they're the same. But if we say it for one, it's the same for the other. In the marginal case, the probability of y0 is 1. In the A1 case, it's still 1, because these are both 1s. In the A0 case, it's still 1. So y0, the distribution does not change depending on whether we're conditioning on A or not. And therefore, A and y0 are independent in this subsample. Now the question is, are they all, or in this subpopulation? The question is, are they also independent in this subpopulation? So let's check. By the same argument, so in this population, it's not all 1s, it's actually all 0s. But in this subpopulation, we have that the distribution is probability of y1 equals 1 equals 0 for marginally, but also conditionally, because in the y1 A equals 1 case, the probability is 0. A equals 0 case, probability is 0. So we have the same distribution, conditioning on A equals 1, A equals 0, and marginally. So that tells me that A is independent from y0 in this subpopulation. And since they're independent in both subpopulations, indeed, we have this statement here, which is that y0 is independent of A in any subpopulation of x. That is true. So next question is, what is the expected value of y given in the subgroup of people where e equals 0 and x equals some x, added as a column? So what I mean by that is, so x has two values, right? 0 or 1. So let's compute for x equals 1. Let's put it up here. X equals 1. Okay, so that's saying in this subpopulation and then this subpopulation. So really we just have this is the only thing that we're averaging. What's the expected value of y? And let's just add y here. We know what that's going to be. So this is 1, because it's just the average of this number, right? That's the only population we're looking at. Now let's compute expected value of y given a equals 0 and x equals also 0. So that is a equals 0, x equals 0. It's these two rows. So it's the average of two zeros, which is 0. So we can add that here. So I'm going to add a column, mu, I'll just call that mu y of x 0. And now I'm just going to plug in the x that I see here. to see which of these numbers I should put. So for x equals 1, I'm getting 1. For x equals 1, I'm getting 1. X equals 1, I'm getting 1. And these ones I'm getting zeros. And now what is the average of this column? So here this is mu y of x 0. What's the average of that column? Well, 3 1s, 3 zeros, 1/2. Okay? Which again, you can compare it to the average of y0, which is 1/2. And similar, if we were to do this again for y1, so we can change here a equals 1, a equals 1. These numbers actually don't change here because here we're looking at the a equals 1, x equals 1 subpopulation. So you get 2 1s, 1. And then here we're looking at the a equals 1, x equals 0 subpopulation. So average of 0 is 0. So if we had changed this to 1, that would have been the same. So we actually get that mu y of x1 is equal to mu y of x0. And so when you take the difference of them, you're always going to get 0, which is in fact the true causal effect. And if you remember from the previous slide, if we were just looking at the naive ATE, we were getting like a 1/3 effect when really nothing is happening here. But if we instead stratify by x and we look in the subpopulation where x equals 1 and then in the subpopulation where x equals 0, and we're only doing the comparisons in those subpopulations, and then we aggregate those together. So this is the aggregation is effectively happening here, right? Because I'm putting in these ones. How many ones are there? 1/2, and these are also 1/2 because that's the probability that x equals 1, and this is the probability that x equals 0. So here I wrote out this value for every single person, but I could have gone from here and just used total expectation to say what's the expected value of just x, right? So averaging over x here. If I call this mu y of x, this is by total expectation mu y 0 times the probability that x equals 0 plus mu y of 1, probability that x equals 1. These are both 1/2. So what I'm doing is I'm weighting the conditional mean in this group by 1/2 and in that group by 1/2. And if I were to look at the difference of this minus the mu 0 case, I would have this minus the mu. I should have written this a little bit more clearly. Mu y x1 0 1 1 1. Okay. So what I was trying to say here is that I could write this in as like a mutate, right, to get this new column here, and then I just average over that column. Or I could do this with total expectation, where I take the value of this function in this group and the value of this function in that group, and then I just weight them by the probabilities of each group and add them together to compute this total expectation. It's the same thing. So the key again is that comparing this slide to the previous slide here is that when we did this and we looked at that naive group mean, we were getting an effect. But that's because we were looking at all the data together. Whereas if we looked at the data subsetting to x equals 1 and x equals 0, because we have this conditional independence, in each subgroup of x, we essentially have a randomized trial. So we can analyze that as if it were a randomized trial using the kind of naive estimate within each subgroup. All we need to do is to get the causal effect in the total subgroup, in the total population, is to aggregate those RCT results, right? But to get to the result in the total population, you need to weigh the effects in the subpopulations by how many people are in each subpopulation. And that's exactly what we did effectively. So when you see this, that's kind of what this is doing. This is so I was doing it only for one treatment arm, but if you are asking about, okay, this is like y a equals 1 in some subpopulation minus expected value of y given a equals 0 in this subpopulation, right? This is like the RCT result in that subpopulation defined by x equals x. And then to get to the overall population effect, you need to take the average of those like randomized trials that you're doing in each population, but you need to weight them by how many people are in each of them, relatively speaking. To be clear about one thing, randomized trial doesn't not necessarily mean that, or when I say randomization or randomized trial, it doesn't mean 50-50 randomization. So here's a case where in this subpopulation, we have 2/3 of the people are getting the treatment and 1/3 is not. But and in this subpopulation, we have 2/3 not getting the treatment and 1/3 who do. So randomization doesn't mean flip a coin that's 50-50. It just means you flip a coin. So here, that coin happens to have 2/3 probability of heads. Here it happens to have 2/3 probability of tails. But that doesn't matter because the key thing is who is getting the treatment is randomly decided in each subpopulation. So who gets these 2 1s and who gets this 0? That's pure chance. It doesn't actually matter how many 1s and 0s there are. So here's an example in R going through this. So let's say we make this population data frame, and we have X as a uniform. So we're really doing this, but more elaborate, right? We don't just have 6 people in our population, which is ridiculous, but we have hundreds of thousands. If we have our data frame, X is a uniform random variable, so this might represent some continuous covariate like age. A is our binary exposure, and it depends on this covariate. So the bigger this is, the more of a chance you have of getting the exposure, and the smaller this is, the less of a chance you have of getting the exposure. And then we have our potential outcomes. So Y0, if you're not treated, then your outcome is negatively related to X. If you are treated, your outcome is related to X squared minus X. Those are the mean outcomes, but there's some variability with the normal. And then Y is just which of these do you observe given A. So let's just calculate, since we have the population data frame, the causal population data frame, it doesn't really matter what the details are. I can calculate the causal average treatment effect by just taking the mean of Y1 minus the mean of Y0 in the population data, and the number I get is 0.332. And I can also take the naive ATE by taking the population and then just looking at the mean of Y in this subgroup minus the mean of Y in that subgroup, and I get a different number. So that is a difference of about 0.05 in this case. But instead of doing that, this is the wrong answer essentially, right? So here's the causal ATE again. Instead of doing that, I can compute this observable ATE, not the naive ATE, but this observable ATE, where what I do is I first say, what is the conditional mean function? So here I called it mu, and it's this function of x and a. And if a is, so let's look at it for the case that a is 0. So if a is 0, then this part is gone and it's just minus x. So that corresponds to this conditional mean here. If a is 1, then this stays. So we have x squared minus x, which corresponds to x squared minus x, which is the conditional mean of y1. So this mu, if you have a to be like little a, 0 or 1, corresponds to the conditional means of y0 and y1. And indeed, that is the conditional mean of y, because y is y1 when a is 1 and is y0 when a is 0. So you can construct that conditional mean function for y, given a and x, by just looking at what it is for y0 and y1 and saying if a is 1, then take this conditional mean. If a is 0, take that conditional mean. So this is the conditional mean function for y. Now what we're going to do is take the population, and like we did in this example, we will add a column that represents the value of mu0. So it's just a mutate. I'm looking at the value of x in each of the rows of this data frame here, and I'm plugging it into this mu function. And I'm saying also fixing a to be 0. So you can think of this as like, what is the value I think I would have observed for this person had I not treated them? And so it's kind of like an approximation for y0, or an expectation, right? Similarly with mu1, what is the value of the outcome that I think I would observe for a person with this in this stratum had I treated them? And you generate that. So you can think of those as two kind of like counterfactual predictions. And then you take the mean, you take those two columns, you subtract the one from the other, and you take the mean of that, or equivalently the mean of mu1 minus mean of mu0, same thing. And you look at that, and you get the same answer, the causal ATE and the observable ATE. So naive ATE bad, observable ATE good in this situation because we don't have randomization between A and Y, but we do have conditional randomization, which we can see by looking at this. If you were to draw the DAG of this, you see that X goes into both A and Y0, Y1. And so if we want to block the flow of information from A to Y0, for example, we just have to condition on X. So A is independent of Y0 given X. Same with Y1. Okay, so let's zoom out a little bit from the math and think about it a little bit more conceptually. So let's say I want to know the effect that prior incarceration has on early onset Alzheimer's. You design a 40-year study where we track 10,000 randomly selected 20-year-olds. We record if they're ever incarcerated in their 20s, and then figure out whether or not they develop Alzheimer's before they are 60. And the plan is just to compare the percentage of Alzheimer's between the previously incarcerated and non-incarcerated populations. My question to you is, what's wrong with this? It should be clear, I hope, that there's potentially a lot of confounding here. So the kinds of people who are likely to be incarcerated maybe are also likely to develop Alzheimer's for other reasons, right? It could be that, growing up in certain neighborhoods, you're very likely to have interactions with the police, and it's also maybe high stress in childhood, which contributes to Alzheimer's. And so it's not really the incarceration that's causing it. It's just growing up in a kind of shitty situation that's causing both of those things together. And so it's hard to pick apart that if you're just looking at these associations kind of marginally and computing this naive ATE. So overall, what's wrong with this? Well, you have to adjust for confounding. And maybe, neighborhood that you grew up in is a very important confounder. There's probably many, many others that you can think of that are things that you would want to condition on. In general, stuff like this gets published all the time. Maybe not quite like this, but there's plenty of things where you're not adjusting for enough confounders. And it's always the case that you're not adjusting for all the confounders that you could have. There's an infinite number of confounders and things that you could be trying to adjust for or condition on, and you just don't have them, right? Maybe it's too hard to get them. But in this setting, I would say if you're doing a 40-year study, this is probably millions and millions of dollars for 10,000 people. I mean, this is an insanely large, expensive study. There's no way you could justify doing this if you're not going to, be very attentive to collecting every kind of information that you can to really get at this causal link. Otherwise, this is just a colossal waste of money. So I would say for the smaller and more kind of ad hoc and exploratory your study is, the less it matters whether you're being super, super careful. But the larger and more expensive it is, you really do have to pay attention. All right, so let's zoom out again. We now have conditional randomization. We've shown that we can identify causal effects in cases where we believe that we have enough confounders that we have conditional randomization, that we have randomization in substrata of the population. That's not always, but generally considered to be a weaker assumption, right? Because if it's crazy to think that, for example, incarceration is randomly assigned in the population. It's not. But maybe if you measure enough stuff right? If you condition on somebody's educational history and all sorts of stuff, so in the group of people who all have the same kind of education, the same kind of neighborhood, grow up in the same neighborhood, the same kind of interactions with the same kinds of people, whether or not they, end up in the justice system, maybe that's as good as random, okay? If you condition on enough stuff, you can try to believe that. And so my point is that the set of distributions where this conditional randomization holds is probably, in some sense, bigger or more plausible than the set where this marginal randomization holds. They overlap. There's many cases where if you have marginal independence, you have conditional independence, but there's also some cases where actually you don't. So you can have conditional independence when you don't have marginal. You can have marginal when you don't have conditional. But it's generally thought that in practice, these cases here are very, very rare. And so conditional randomization is generally thought to be weaker than randomization. But it's not all encompassing, right? Like we've talked about, there's distributions where there are plenty of distributions where you don't have this conditional randomization because you haven't measured enough stuff X. That's one way to think about it. Of course, statistically, you're not asking from the perspective of the distribution. There's no question of what is measured or not measured. It's just this is the relationship between these variables. And so one way to think about it is there are distributions where there are relationships between A and YA where it's not conditionally independent, right? That's obvious. You can always come up with one where that's the case. But thinking about it in terms of practice, why should that not be the case? It's just because you haven't measured enough stuff X to make it the case, right? So ideally in some kind of thought experiment, you would presume that if you measured enough baseline, if you knew enough about all the people, if you had infinite data, if you knew enough about everyone, then you could make it so that the outcome is basically, or the exposure is given as good as random in each subpopulation. But generally we don't. So point being, observed confounding is okay. If you have this confounder, if you measure it and you have it in your data set, that's okay because we can just condition on it and then compute the causal effect like this, right? Where we just get we use these conditional means to get the within each subpopulation, we compare as if it's an RCT, and then we aggregate to the whole population by averaging over all of those subpopulation RCTs. That's fine. But what's not fine is if you have unobserved confounding. So if you have some variable affecting both of these things, and it's not in your data set, that induces the dependence between A and YA, right? Because now if you're conditioning on X but not on U, your information is still getting from YA to A. And that's no good. So that's why I say conditional randomization to get at the kind of like practical, like, okay, we're essentially assuming we have an RCT in each subpopulation, but another way to say that is that there's no unobserved confounding. If we had an unobserved confounder, that would induce this dependence, and it would mean that you don't have this conditional independence, right? So if you hear people say, my assumption is that there's no unobserved confounding, that's the same as conditional randomization. Whichever way you want to think about it, both are useful. I will note that no unobserved confounding does not mean that you can't have things that are affecting A and Y that are not measured. There's always stuff that affects the outcome that you're not measuring. There's always stuff that's affecting the exposure that you're not measuring. But it's okay as long as those two things aren't the same thing, or there's no path that connects them, right? In some kind of like backdoor path. This is not okay. This is fine. So again, to emphasize the stratum interpretation, no unobserved confounding means that you have enough strata, or the strata are fine enough to create randomization. So if I measure just one variable, I can cut up my population along that variable. But maybe that's not enough. Maybe I also need to cut it up along another variable. Maybe I need to cut it up along a third variable. And you need to get small enough groups there so that in each subpopulation you have that randomization. And that might not be the case for some small number of slices. So let's keep thinking about this. We're studying the effect of high sugar versus low sugar diet in early adulthood on the rate of stroke in middle age. what are some possible confounders that would be easy to measure or find in registry or electronic health records data, or whatever kind of data you're used to thinking about? Just think about that. What do you have there that would be useful to study this question, and what would be difficult? So for the first one, I work mainly with electronic health records data, and if I'm interested in like sugary diet, the rate of stroke, what's a possible confounder? So what is something that could affect both what kind of diet you had in early adulthood and your rate of stroke? So I'm thinking, the kind of household that you grow up in, like if your parents eat a high sugar diet, then you're going to probably eat a high sugar diet for sure. So that's something that for sure affects the outcome. The question is, does it affect the risk of stroke independently of the effect through the exposure? And I think that there's definitely some plausible connection there, right? Let's say that, for example, let's say there's a genetic factor, right? If you're, or it doesn't have to be necessarily genetic that like a gene makes you more prone to eat high sugar diet. But let's say that there are certain populations that culturally their food has a lot of sugar in it, but those populations also, for whatever reason, have a higher risk of stroke. Okay, then which of these kind of subpopulations you're in would affect both, whether you have a high sugar diet, and would affect your risk of stroke. So that's a possible confounder, just this population structure, and that might be difficult to find in registry or electronic health records data. So, for example, if it's this population structure stuff having to do with like childhood diet, typically electronic health records data or registries, you're going to get like race, right? Like U.S. government census type race, which is a very artificial and coarse construct that doesn't reflect something like people's diet, right? Whereas, like, let's say what you might want to know is like, okay, are you from Haiti? Are you from a particular part of India that has a particular kind of dessert that's very high in sugar that people are eating a lot, right? This much more granular detail not really was captured in electronic health records data for the most part, or registry data. And that would definitely be a confounder. So those are some things that would be very difficult to measure or find. Confounders that would be easy for this problem. Not a lot comes to mind off the top of my head. Certainly, like you could have some kind of childhood diseases, like rare diseases that might impact your tastes or preferences, and also impact your overall disease state through your life and impact stroke. That would definitely be captured in health type records if you were around when you were a kid in the same kind of health system, because a lot of these data are super fragmented. So anyways, there's probably many more that you can think of or reason about. I'm not saying that my reasoning is perfect for this problem, because I'm not actually a domain expert, so this is not what I'm paid to do. But this is the kind of thing that you should be paid to do eventually as public health professionals or domain professionals. You should be thinking about things in these ways and understanding that what's in your data is probably not what you want most of the time, and understanding how to what effect will that have on your estimate. What kind of bias is introduced by not being able to measure this? Because effectively, if you don't have these confounders, you don't have the randomization, right? In each subgroup, you don't have enough subgroups to have that randomization, and so your causal effect is not going to be causal. And you can start to reason about, okay, well, if I included this variable, how much better would it be? So maybe in the next study, I could go get that variable because I think that's what's missing. Or I can compare these two studies that I'm reading. What's different about that one versus this one? Which one is more likely to be trustworthy? A really important point to make here is that most causal assumptions, they're not testable. So you can't really tell if you're missing a confounder. You just can't. Because the independence assumption is not between A and Y, which is what you observe. It's between A and Y1 or A and Y0. So you can't look at, for example, the correlation between A and Y and say, or A in some subgroup or something, and say, oh, they're independent or they're not, or I think they're independent or I think they're not independent based on some correlation. I mean, you couldn't anyways, you couldn't like conclusively determine that, but you could say, okay, there's evidence that they are or that they aren't in general. But certainly in this case, you don't even have the variables that you would want to compare. You don't have y1, you don't have y0, you just have y. And so you can't really answer this question with just the data. You cannot say, oh, let me look at the data and that'll tell me if I'm missing a confounder. Or alternatively, let me look at the data and tell you if this is a confounder. That's messed up too. You can't test that something is a confounder or not and then say, oh, it's not, I'm going to leave it out of my analysis because then I'm going to get a nicer p-value. Like, absolutely not. And you see that all the time. So you can't do either of these things. The data can't tell you about confounding. You have to think about confounding. You have to do the kind of stuff that we're doing here, where you have to use your domain knowledge and your understanding of the field, social contexts, biological contexts, and that is what's going to inform what you should be thinking about to adjust for or not adjust for.